students, today we are discussing on the topic or the point what is meant by the Euclidean metric space. So in order to study the Euclidean metric space, we have to know about what the Euclidean space. Now what is meant by the Euclidean space? What is space? Space is nothing but any set with an structure or with an operation. What is meant by the space? Space, it is a structure contains two things, two elements. First one is a set and then an operation. Likewise, G star, what? This is a group, this is a binary operation. It is a structure. Metric space, vector space. So one set associated with some operations, it is called as a space. Now what is meant by the Euclidean space? In order to study the Euclidean space, we should know about what is meant by the vector space. Vector space is nothing but the non-empty set V. What is meant by the vector space? Non-empty set V together with two operations plus and dot defined over the field F which satisfies some certain condition. It is called as a vector space. What is meant by the Euclidean space? Because this definition is studied in the linear algebra. Okay, now what is meant by the Euclidean space? Euclidean space is nothing but the vector space. Vector space, how? R over R is what? A vector space. It is called vector space. Now this is in one dimension. So one can define a vector space in two dimension also. So R2 over R is what? Two dimensional vector space. R2 over R is what? Two dimensional vector space. Similarly, R3 over R is three dimensional vector space. Similarly, one can define Rn over R is n dimensional vector space, and this n dimensional vector space is called Euclidean. It is called what? Euclidean space. Now what are the elements of Rn? What is the Rn? Rn is nothing but R cross R, Cartesian product of real numbers. Okay, now if any element x belongs to Rn, what it means? Now जर समजा x हा Rn चा मेंबर आहे म्हणजे काय? X is equal to what? x1, x2 and so on xn. So this has a tuple, n tuples. It has two ordered pair. It has triplets. Three elements x1, x2, x3, three dimensional. This is two dimensional. This is three dimensional. Likewise, this is an n dimensional. And this Rn is called as an Euclidean space. So Euclidean space is particular case of a vector space of n dimensional real numbers. So what is meant by the Euclidean space? Euclidean space is particularly we can say that Rn over R is called Euclidean space when it has a metric defined with the help of the function. With the help of the function, if suppose x comma y belongs to Rn, then x is equal to what? x1, x2, x3 and so on xn. Similarly, y is equal to y1, y2, y3 and so on yn. Then the Euclidean distance is defined like this: d of x comma y is equal to square root of x1 minus y1 bracket square plus x2 minus y2 bracket square and so on, xn minus yn bracket square is wholly completed in the covered under the square bracket. So this is what Euclidean distance, and Rn over this Euclidean distance d is called Euclidean space. Now two-dimensional metric space is also, that is, if n is equal to 2, it is a Euclidean space. For n equal to 3, it is Euclidean space. For any n is equal to k, it is an Euclidean space. It is a general nomenclature for this vector space Rn over R. So this is called as an Euclidean space. And what is mean by the Euclidean metric space? This is what Euclidean metric space. This is just simply a Euclidean space. This is simply a, here is no need to define the metric. But whenever I define a metric on Rn with the help of this function d of x comma y, it is called as an Euclidean metric space. Now what is, so I will give a general or a short focus or flash on what is meant by the metric space and its properties. Then we will further define or discuss on open set in Euclidean space, closed set in Euclidean space, what is the neighborhood, definition of neighborhood in Euclidean space, and some examples related to that points, what that is neighborhood, Euclidean space and metric space. Okay, so let us start with the definition of metric space. What is the definition of metric space? What is the definition of metric space? Let capital X be a non-empty set. Capital X be a non-empty set and the distance function d from x cross x to R are non-zero real numbers or positive real numbers. Sorry, instead of non-zero real, positive, because distance between two single that is distance between point to itself is 0. So distance may be 0. So without loss of unit, we can say that R or R plus union singleton 0. Let X be a non-empty set and the distance function d of x comma y is called metric if the following conditions get hold. First condition is d of x comma y is greater than or equal to 0 for all x comma y belongs to capital. That is, distance is never 0. It is always non-negative number. That is, distance may be 0. Or distance may has any positive value. Okay, that is, distance never be negative. So second one, distance between 2 points is 0 if and only if these 2 points are equal. That is, if distance between 2 points is 0, what it means? These 2 points are nothing but coincide with each other. Okay, so distance is 0 if and only these 2 points are equal. Third one, distance is symmetric. d of x comma y is equal to d of y comma x. Distance is always symmetric. Fourth one, distance between the 2 points x comma z is less than or equal to d of x comma y plus d of y comma z. This is the triangle inequality property. That is, if we have these 2 points x and z, this distance is less than or equal to, if I am considering this x and z, and suppose third one is 2 point, then the distance between this plus this is always greater than or equal to the distance between these 2 points x and z. This is called triangle inequality. This is called symmetric. This is called what? This is positivity and this is what? Nullity. So distance is 0 if and only these 2 points are equal. So this is the definition of metric. This is the definition of metric, and the space, if x is a non-empty set and d is defined on x, then the ordered texture xd is called what? It is called metric space. In the ordered structure xd is called metric space. So let us some examples of the metric space or metric. Let x is equal to r and d of x comma y is equal to modulus of x minus y. So x is equal to the set of real numbers. X is equal to what? The set of real numbers, and d of x comma y is equal to what? X minus y. Then we have to check that this is a metric or not. So it is very easy to show that all the conditions get satisfied by this function. So we know that modulus is always non-negative. So mod of x minus y is greater than or equal to 0 for all x comma y, implies that d of x comma y is equal to 0. Sorry, greater than or equal to 0 for all x comma y. Again, modulus of x minus y is equal to 0 implies and implies what? X minus y equal to 0 implies and implies x equal to y. But this is what? D of x comma y is equal to 0 implies and implies x equal to y. Third condition is also, we can prove that by using this mod of x minus y is equal to what? Mod of y minus x. And by using this properties of modulus, we can easily show that this fourth condition also. Okay. So what is the fourth condition? X minus z. We can write this as x minus y plus y minus z. And using the properties of modulus, we get x minus y plus modulus of y minus z. So distance between these 2 points is less than or equal to distance between these 2 points, the distance between these 2 points. So all these properties get satisfied by this function. D of x comma y is equal to modulus of x minus y. So this xd is a metric space. So this is the xd is a metric space defined in one dimension. So this is one dimension Euclidean metric space. This is one dimensional Euclidean metric space. One dimensional Euclidean metric space. Next example. Let capital X is equal to R2. Capital X is equal to R2 and D of x comma y is equal to square root of mod of x1 minus y1 bracket square plus mod of x2 minus y2 bracket square. x1 minus y1 bracket square plus x2 minus y2 bracket square. Now, in order to check all these conditions, so first three conditions are very easy to prove, that is positivity, symmetricity and non-negativity. All the three conditions are get satisfied by this function here, by this function d. Okay, fine. First we have to prove that what? D of x comma y is greater than or equal to 0. We have to show this. D of x comma y is greater than or equal to 0. We have to prove this. So in order to prove this, we know that x1 minus y1 bracket square plus x2 minus y2 bracket square. This quantity is what? Square quantity. It means that it is non-negative. This is also non-negative. Addition of two non-negative number is also non-negative. So it is greater than or equal to 0. So square root of this quantity is also greater than or equal to 0. What it means? D of x comma y is greater than or equal to 0. Isn't it? So we can easily show that d of x comma y is non-negative. Similarly, we can show that nullity d of x comma y is equal to 0 when if and only x equal to y. This property is also very easy. So here we have to this. Now assume that d of x comma y is equal to 0 implies that square root of x1 minus y1 bracket square plus x2 minus y2 bracket square is equal to 0. Squaring both sides we get x1 minus y1 bracket square plus x2 minus y2 bracket square equal to 0. Now these are the two non-negative numbers and addition of two non-negative number is 0 when these two numbers are 0. So this x1 minus y1 bracket square is equal to 0 and x2 minus y2 bracket square is equal to 0 implies that x1 is equal to y1, x2 equal to y2 implies that x equal to y. So this is what nullity, this is what positivity. Similarly, we can prove this symmetricity of this function d of x comma y. Now, last one, how to prove the triangle inequality. How to prove the triangle inequality. How to prove the triangle inequality? Let x, y, comma z belongs to R2. So x is equal to x1, x2, y is equal to y1, y2, and z is equal to z1, z2. Then d of x comma z is equal to square root of we can write this x1 minus z1 bracket square plus x2 minus z2 bracket square. It can be written as summation I runs from 1 to 2 xi minus zi bracket square xi minus zi bracket square summation I runs from 1 to 2. Now write this as xi minus yi plus yi minus zi bracket square raised to 1 by 2. Here raised to 1 by 2. Now by using Minkowski's inequality, we can write directly it as summation I runs from 1 to n, 1 to 2 xi minus yi bracket square xi minus yi bracket square raised to 1 by 2 plus summation I runs from 1 to 2 yi minus zi bracket square raised to 1 by 2. So this is nothing but distance between 2 points x and y, and this is nothing but distance between y and z. So it is less than distance between x and z is less than equal distance between x y and distance between y z. Addition of these two points. So the triangle equality gets satisfies. Hence this R2 with this matrix D forms a matrix space called as an Euclidean space in two-dimensional vector space. So it is called as a Euclidean matrix space. So I have just used here Minkowski's inequality. So there are the two inequalities, Shaw's inequality and Minkowski's inequality. Shaw's inequality used for the product of 2 points x and y, and Minkowski's inequality is used for the addition, to separate the addition. In the notes you will get all the properties, that is all the inequalities, Shaw's inequality and Minkowski's inequality. Okay. So now further we proceed. So some more definitions, that what is mean by the norm, what is mean by the matrix inner product space. So first we will define the inner product space. First we will define what is mean by the inner product. Inner product is nothing but a scalar function denoted by this notation, defined from x cross x to r by, if x comma y belongs to capital X, the inner product of x comma y is equal to summation is from 1 to n xi y. This is what definition of inner product. This is what the definition of inner product. And what is the definition of inner product space? Actually this inner product is nothing but, or it satisfies the properties of the metric space. So it is nothing but the metric. One kind of metric. What is metric? Actually metric is what? Distance function. So from one village to another village, there are the several routes to approach one city to another city. So depending on the roads or the way, we have the different distances. So depending on the functions, we have the different metrics. We have the different distance functions. So these are the, so this is one of the metric, one of the distance function, and with this distance function forms a metric space called as a inner product space. Called as a inner product. This set X with this function forms a metric space called as a inner product space. Forms a metric space called as a inner product space. Next, the definition of norm. Let X be a metric space and small x belongs to capital X, then norm is denoted by this notation x and defined as summation from 1 to n xi square. Now, this is what definition of norm.